So last time we were discussing this operation of space inversion or parity on the free fundamental fields, relativistic quantum fields. Okay, so, sorry, classical relativistic fields that Planck, Gordon, Dirac, and Maxwell's field. Today, we will discuss another kind of transformation. So, space inversion was just flipping the sign of the space coordinates without changing time. That was the space inversion or parity operation. So that operation deals with is a special kind of space-time transformation because it changes space, but it is a discrete transformation. It jumps from x, y, z to minus x minus y minus z. Okay, so this was a discrete transformation. Today we will study another kind of discrete transformation, but which does not deal with space-time coordinates. Okay, it is some internal transformation. So let's begin. We know that these subatomic particles, which have different intrinsic natures or dimensions, they are characterized by different types of intrinsic quantum numbers: electric charge, lepton number, baryon number, strangeness, color, beauty, truth, etc. Now we will adopt a general nomenclature as charge for all these intrinsic quantum numbers. So all these intrinsic quantum numbers will be collectively called by this name charge. So when we say that particles have different kinds of intrinsic quantum numbers, we say particles have different kinds of charges. This is not electric charge is one kind of charge. Lepton number is another kind of charge. Baryon number is another kind of charge. So from now on, in the context of particle physics, the word charge will mean intrinsic, all possible intrinsic properties of that particle. Okay. Now we want to construct a theory of subatomic particles, that is leptons and baryons and mesons, etc. And if you look at the fundamental particles, they are leptons and quarks. Now these particles, since they are relativistic and macroscopic, we started by investigating first the behavior of relativistic fields, phi, psi, mu, etc., which are relativistic fields, as well as, since becoming their fields, they can describe the microscopic world. Okay. However, since these subatomic particles are to be described by these relativistic fields, somehow the charge of the relativistic particles, charge means this collective charge, all possible charges or intrinsic properties of the relativistic particles should somehow be embedded in or should somehow be contained in the field description. So these fields will somehow so what I have written, there must be an inherent aspect of the description of the fields which can be linked to the charges of the particles which is described by this field. Okay, so this aspect of charge of these particles must be somewhere in the description of the field. Okay. Now, so we have to investigate how this aspect that charges of these subatomic particles are embedded in the description of the relativistic fields. We have to investigate this. To investigate this, we have to proceed by observing how these fields respond when I make a transformation of charges. Okay, so thereby we want to probe to know how these fields will contain as information the charges of these particles. Okay. And this, so we proceed by observing how these free fields respond to the transformation called charge conjugation. So charge conjugation is a transformation which is defined as transformation of the fields which amounts to flipping signs of all the intrinsic charges of the particles associated to this field. Okay, so there are subatomic particles. They are represented by different kinds of fields. Now, charge conjugation operation means if I do that operation on these fields, this field will represent the particles which have opposite charges to these particles. Okay, so if psi represents a particle, say this particle, then if you do the operation of charge conjugation on this field, that means this charge conjugated field will represent antiparticle of this particle. Clear? So this is the definition of charge conjugation. We will see soon how in terms of field it can be defined, but this meaning of this charge conjugation is that the fields representing some particles, you do a charge conjugation operation on this field, then this new field will represent fields which are antiparticles of this field psi. This is the operation of charge conjugation. And since all kinds of intrinsic charges for a particle and antiparticle are opposite in sign, therefore charge conjugation means obtaining the field from a given field which will represent the antiparticles of the particles which are represented by that field. Clear? So if you do the charge conjugation operation at the field level, your particle description changes from particle to antiparticle. Any questions? So this is the definition of charge conjugation. Now let's look at, this is this charge conjugation is a bit different kind of transformation. You will see soon that it is not a space-time transformation. Because of that, it has very intrinsic inherent complications. So let's look at what do you understand by charge conjugation of a scalar field. Now a scalar field phi can be a real scalar field, it can be a complex scalar field. Suppose, let's take for the case of a real scalar field. So just a minute. Okay. So if you do charge conjugation of a real scalar field, what does it mean? Now a real scalar field is a scalar field whose Lagrangian is this, whose dynamics is governed by this. The free Lagrangian of a real scalar field is this, or which is basically the Klein-Gordon equation. Okay, so you can look at the Lagrangian or the Klein-Gordon equation. Both are equivalent descriptions of the dynamics of the real scalar field. Okay. Now, try to understand this fact that a real scalar field is a real number. This numerical value of this field is a function that is a real function, not a number. It is a real function, and it is a function of space-time. Therefore, it has only one real degrees of freedom. It is not a complex number, unlike complex scalar field. Neither it carries any Lagrange index. Okay, so it is a single object. It has no components. Neither it is a four component object like Dirac field. So it's this structurally this real scalar field is a featureless object. It has only one feature. It depends on space and time. It has no other indices, no Lorentz indices, no spin indices, okay, no structures in that sense, like 4x1 structure, like that, and it is also a real function. It is not complex. This function phi is not complex. So we said this real scalar field is otherwise a featureless mathematical object. It carries the most simple form of space-time dependence because it is a scalar. It is invariant under Lorentz transformation. The space-time dependence is also the most simple space-time dependence you can think of in terms of Lorentz transformation. It is not a vector, not a spinor. Okay. So in this field, you find no mathematical structure or no mathematical attribute to which you can associate the internal degrees of freedom of the particles represented by these fields. Do you follow this? You have to understand this, that this scalar field phi is only a function of space-time, and the simple most function of space-time. It has no special structure in this. It has no structure. It is a single function. Neither it is real. It has it has no more than one. It has only 1 degree of freedom. Okay. Because of this, but I said that if you want to do the charge conjugation of this operation of this field, that means we first want to associate these fields represent some particles. These particles can carry some charge. Now, these charges are intrinsic to these particles. Okay, intrinsic charges of these particles represented by some field phi. Now, what aspect of this field should be related to these charges? Okay, but it has because charges are intrinsic, they are not space-time dependent. So field is a simple function of space-time. It has no other structure. If it would have structures or any other internal degrees of freedom, then we could have associated electric charge, intrinsic charges to that aspect. But since phi is a featureless object, in that sense, there are no I have written this here, you can read this letter. So there are no extra mathematical attribute of a real scalar field to which we may intuitively associate intrinsic charges of the particles which it describes. So that means by no way this mathematical object phi, which is a real scalar field, they can represent particles with charges, intrinsic charges, because then there is nothing, no feature in this field which can capture the intrinsic charges of these particles to represent. Therefore, we say real scalar fields can only be described to be used only to describe particles which are spinless and antiparticles of themselves. That means they have all the charges are spinless because they have no other structure, and also there's no other charges. Because of that, this real scalar field can describe only particles which are their own antiparticles and also spinless. Okay, so like spin zero particles which are their own antiparticles. Only those kind of particles can be represented by scalar field. Is it clear?
Yes, sir.
Yes, sir.
Okay. Now, in symbolically we say that real scalar fields does not transform or remains invariant under the operation of charge conjugation. Because if you do the operation of charge conjugation, which means to change the field in such a way that it will represent the antiparticles of these particles which are represented by the fields, then since it has no mathematical feature in it, there is nothing to change. So it must represent particles which are their own antiparticles. Therefore, charge conjugation of phi written as this under C means under charge conjugation, the real scalar field changes to this, which should be equal to this, because it is a real scalar field. It should represent particles and same particles and antiparticles are represented by this scalar field. Okay. Example of this are, so remember, it should be spinless as well as the particles and antiparticles should be same. Those particles are described by phi. So examples are pi 0. You know, pi 0 is a spinless particle. Spinless particle. It has no charges. No charges means it is no electrical charge, no lepton number, no baryon number. Sorry, baryon number 0, lepton number 0, etc., etc. Okay. Other things also, no color, no truth, no strangeness. Pi 0 is not a strange particle. So pi 0 and also Higgs. We will see later that Higgs is a scalar particle which has no other charges. They are the candidates which can be represented by a real scalar field, as we see from the our understanding of the concept of charge conjugation. Now see, photon is also chargeless in that sense. It has no electrical charge, no other charges also, lepton number, proton, baryon number, etc., strangeness, etc. All are 0 for photon. But photon has a spin. Okay, so though photon is its own antiparticle, because it has a spin, because of that, phi real scalar field can't describe it. Okay. Let's come to the complex scalar field. Now, a complex scalar field is described by this Lagrangian, where phi star for del mu phi star del mu phi. Okay. Now, see, a complex scalar field has at least one mathematical attribute extra other than its space-time dependence. That is its complex nature. That means it has 2 real degrees of freedom, because the complexity of this phi makes it to carry some intrinsic mathematical aspect which one can think to associate with these intrinsic charges of these particles represented by this field. Okay, now you see, we have seen this. A complex scalar field can be written as in this way, in terms of 2 real degrees of freedom, like this, where phi 1, phi 2 are real scalar fields. Phi 1 is, you can write phi 1 and phi 2 in this way. Or instead of describing the complex scalar field in terms of the 2 independent real scalar field, you can choose phi and phi star as independent fields to express the dynamics of represented by phi 1 and phi 2. Okay. So for complex scalar field phi, these 2 independent equations of motion which express explicitly the 2 degrees of internal degrees of freedom is this. Okay. So at least complex scalar field has 2 internal degrees of freedom. So I'm reading out. Thus, apart from this space-time structure, the complex scalar field also involves 2 internal degrees of freedom due to its complex nature manifested through 2 independent modes of fields, phi and phi star. We now have some extra mathematical attribute owing to the complexity of the scalar field, to which we may intuitively think to connect the internal or intrinsic charges of the particles described by the complex scalar field. Okay. Now, how to make this association? How we should associate the internal intrinsic charges to, or the operation of charge conjugation to the complex nature of the field. Okay. So we initiate this by demanding that when the charge conjugation operation is applied on the complex scalar field phi, the result will be something which is related to phi star, because phi and phi star are only deals with internal degrees of freedom. So we say that, and vice versa. If you do charge conjugation on phi star, you will get something which can be expressed in terms of phi. Or in other words, if a particle is described by a complex scalar field phi, its antiparticle should be described by a field which is related to phi star. This is our assumption. Assumption means we structure the nature of the, so we impose the condition that the complex nature of the field somehow carries the information of the charges contained by the particles described by the field. Okay. So we say that under charge conjugation, a complex scalar field phi x, which transforms in this way, should be equal to some number into phi star. In general, it is a complex number. I don't know what is this number, but it should be related to this. That's how we first make this is a postulate, which is we are associating a charge conjugation operation to the complex nature of the fields by this equation. So there are two internal degrees of freedom. Now, since charge is an internal object, so we make this association without any loss of generality. And you have nothing else to which you can connect the charge conjugation operation in this field of this field. It is only the complex nature is the only mathematical extra mathematical feature which a complex scalar field has, other than its space-time dependence. Now, charge conjugation will not affect space-time coordinates, so all these x's will be same. Only phi becomes eta c into phi star, where eta c has to be determined. Okay, and but to determine eta c, we have to again make a postulate which will not disturb any observed result or reality, and which is the postulate we made earlier for also for finding arity transformations. The postulate we make here is that the free Lagrangian of the complex scalar field should be invariant under charge conjugation, because free Lagrangian is something which is never observed, which you can't observe in laboratory. Okay, whose effect you can't observe. You can only observe the effect of interaction Lagrangians. So you can make your, you can model your free Lagrangian in whichever way you find useful, but so long as it should respect all the requirement of being Lorentz invariant. Only that is the only requirement. Okay, so now assuming that this Lagrangian is invariant under charge conjugation does not affect its Lorentz invariance, because Lorentz invariance deals with space-time transformation. Charge conjugation is an internal transformation. It doesn't affect space-time. So under charge conjugation, L goes to LC, which should be L. So L is invariant under free Lagrangian of complex scalar field is invariant under charge conjugation operation. That is also that postulate we make. Using that postulate, we can find eta c, because if you take L equal to LC, now LC is the charge conjugation of L, which you can write in terms of the charge conjugated field phi c. Okay, both are equal, so you see this equation. This is the Klein-Gordon Lagrangian, complex Lagrangian for phi c and phi. And if you put phi c equal to eta into phi star, okay, in place of phi c, you will see that in place of phi, sorry, this is a mistake. There is a mistake here. Phi c should be eta c into phi star, and so eta c into phi star. There is a star here, so it's star. So it will be eta c star phi. Okay, so other lengths are correct. So this will give you mod eta c square equal to 1. That means eta c is a phase having this unitary form. Okay. So we can see under charge conjugation, a complex scalar field transforms in this way, where eta c is a phase. This is the charge conjugation transformation of a complex scalar field. A real scalar field does not transform under charge conjugation. A complex scalar field changes under charge conjugation in this way. It becomes its complex conjugate, and there is an arbitrary phase factor multiplied by it. Okay. So if a particle is described by a complex scalar field, its antiparticle should be described by this field, phi c equal to this. Okay, so eta c, where eta c is a phase. So whenever you do charge conjugation on a field, Klein-Gordon field, it will be its complex conjugate. And real scalar field are their own complex conjugate. In that sense, a real scalar field does not transform. Clear? So for complex scalar field, phi and phi c are not equal, because one is phi, other contains phi star. And for complex scalar field, they are not equal, meaning the charge conjugation operation produces a scenario which is different from the scenario before charge conjugation. That means particles and antiparticles are different. Okay. So what kind of particles are represented by this phi? So phi is this scalar field, a complex scalar field. Because it is a scalar, it can't represent a spin particles. I mean, a non-zero. Particles with spin can't be described by this. So all spin zero particles which have antiparticles, they are described by this field. Okay. So this so real scalar field should describe particles which are spinless and their own antiparticles. Complex scalar field describe particles which are spinless but not their own antiparticles. For example, pi minus, pi plus are spin zero particles carrying non-zero electric charge. Okay, their electric charges are non-zero and they are not antiparticles of each other. They are not is missing here. Sorry. Antiparticles of each other. So they are the candidates which can be represented by a complex scalar field phi and its complex conjugate phi star. So phi and phi star describes pi plus and pi minus. Which one describes what? That is up to you. You can take anything. But if phi describes pi plus, phi star should describe phi minus. Phi star means there is always up to an arbitrary phase, eta c into phi star. Okay. Now you look at this. If you remember this meson nonnet, spin zero means meson nonnet. That spin zero means that spin zero makes it relates it to the scalar, Lorentz scalar. And meson means it has baryon number, lepton number 0. Other quantum numbers for particles can be strangeness